In this lesson, we want to talk about graphing exponential functions. So most of you have worked with exponential functions before. They're of the form f of x equals a, which is our base, raised to the power of x, which is our exponent. So notice that you have a variable now in the exponent. And basically, you need to pay attention to these two restrictions on the base. We say here that a, again, the base, is strictly greater than 0, and also a, the base, is not allowed to be equal to 1. I'll talk more about those restrictions in a moment. For right now, I want to talk about the kind of general expectations of what you're going to see when you graph one of these guys. First and foremost, it's not that easy to do because of the kind of limitations of a hand-drawn graph. If you have a smaller base, like 2 or 3 or even 4, it's doable. But when you get into higher bases, let's say use 12 or something like that, well, you're going to have a problem kind of doing this by hand, because if I had something like f of x equals 12 to the power of x, well, 12 to the first power is 12, but then 12 squared is already 144. Okay, so can you plot 2, 144 with a sheet of graph paper? It's going to be really hard to do. So that's why these are pretty difficult to graph overall, and your textbook is usually going to use these kind of smaller bases, as I am going to do as well today. So on your graph, as long as your base a is greater than 0 and not equal to 1, you're going to have these 3 points. So negative 1, 1 over a will be 1 point, 0, 1 will be another, and 1, a will be another. So you can use these 3 points to kind of get things started and then find additional points as needed in order to sketch your graph. Let's say you had something like f of x is equal to, let's just use 2 to the power of x, very common example. Well, if I plugged in a negative 1 for x, f of negative 1 here would be 2 to the power of negative 1, which is 1 over 2 to the power of 1, which is just 1 over 2. Okay, and this is always going to be true, again, as long as a is greater than 0 and not equal to 1. If I had something like g of x is equal to, let's say, 5 to the power of x, well, if I had g of negative 1, well, this is what? It's 5 to the power of negative 1. This is just 1 over 5 to the power of 1, which is just 1 over 5. So it's always going to be 1 over whatever the base is. Okay, in this case, it's 5, so we get 1 over 5. In this case, it was 2, so we got 1 over 2. All right, so we understand that one. So let's go to the next one. And the next two are very easy to understand. So you have 0, 1 as a point. Again, if you raise something to the power of 0, as long as it's not 0 itself, you get 1. And we know that we're not going to deal with 0 because this base here is restricted. It can't be 1, and it can't be something that's 0 or less. So we're good to go. If I raise 2 to the power of 0, I get 1. If I raise 5 to the power of 0, I get 1, so on and so forth. Then the last one is also very easy. We get 1, a, which is the base. So if I raise 2 to the power of 1, I get 2. Right? If I raise 5 to the power of 1, I get 5. You raise something to the power of 1, you just get the number. So using this kind of function here, I would have negative 1, 1 over 2. I would have 0, 1, and I would have 1, 2. Now, these aren't enough points to get the full graph, but it's enough to kind of get things started. Now, before we get into some graphs, I want to talk about the restrictions involved with the base. And I want to tie this into the domain and the range and explain why there's an asymptote at the kind of x-axis. So you'll have a horizontal asymptote there. So let's start out by just listing this guy again. So we have f of x is equal to a, which is our base, raised to the power of x. And the restrictions are that a, the base, has to be greater than 0, and also a, the base, cannot be equal to the number 1. So first and foremost, we're given the fact that the domain is the set of real numbers. So from negative infinity to positive infinity, I can plug in whatever I want for x. There's no restriction. But that comes at a cost to us because we have to now restrict a because we're not restricting what gets plugged in for x. Let's say, for example, we allowed a, the base, to be something that was negative. So let's say we had negative 2, for example. Well, if I plugged in something like 1/2 or 1/4, you'd run into an issue in the real number system. Negative 2 raised to the power of 1/2 is the square root of negative 2, which in the real number system, we don't have that, okay? Same thing goes if I raise it to the 1/4 power or the 1/8 power or something like that. So because we want the domain to be all real numbers, we've got to restrict the base. If we think about the number 0 itself and the number 1, then basically we restrict these because you wouldn't have an exponential function, okay? If you think about 1, let's say you had f of x is equal to 1 to the power of x. Well, no matter what you plug in for x there, if it's negative, 0, or 1, you just get 1 here. So this is basically going to go down to y equals 1, which is just a horizontal line, right? That's not an exponential function. If you had something like, let's say, 0 to the power of x, well, this leads to all kinds of problems. First off, it's only defined where x is greater than 0, okay, because 0 to the power of 0 is undefined. And then if x was negative, let's say it was -1, well, 0 to the power of -1 is 1 over 0. That's undefined as well. And again, if you use negative exponents, that's going to keep happening. So it's only defined where x is greater than 0. And if you do plug something in that range, well, anything you plug in there, let's say you plug 1 or 2 or a million, you're just going to get 0, right? 0 to the power of a million is just 0. So that's why that's restricted. Okay, so that takes care of this and this. So now let's think about the range. Why does it have to be greater than 0? Well, the reason is because if you think about this, and let's just write this as y equals a to the x for right now. And let me just use a practical example and just say 2 to the power of x. Okay, so let's say I was plugging different things in for x and getting a value for y. Let's say I started with a positive number like 2. 2 squared is 4. Okay, so that's positive. If I kept going, I would just get positive numbers if I'm plugging in positive numbers for this. Now, if I plugged in 0, I would get 1. What happens when I plug in negative numbers? Well, if I plug in something like, let's say, -2, okay, then over here, this is going to be what? It's 1 over 2 squared, which is 1/4. If I plugged in, let's say, -5, this is 1 over 2 to the 5th power, which is 1 over 32. So by increasing the negative here, so the way to think about this, because as you move to the left on the number line, the negatives are getting bigger and bigger, right? Bigger in terms of being more negative. That's what I'm saying. They're actually smaller because we're moving left on the number line. But as we get bigger and bigger negative numbers, this guy gets closer and closer to 0, but it will never actually get there, okay? So you can think about 2 to some incredibly large negative number. So 2 to the power of negative, let's say 100,000, for example, something like that. That would be really close to 0, and you can get as close as you want. You could do 2 to the power of -1 trillion if you wanted to, okay, and see what that is. It's going to be really, really close to 0, but you'll never actually touch it. So because of this fact, your y values in this function will approach 0, but they will never touch it, and so it forms a horizontal asymptote, okay, where y is 0, so at the x-axis. Now, if you have a problem where you have some shifting involved, this may change, okay? But generally speaking, if you get the f of x equals just some number raised to the power of x, you're going to have the horizontal asymptote that occurs at the x-axis. Now, let's actually look at the first example. I've already pre-drawn all of these because I'm a terrible drawer and these things are hard to draw. So I'm going to start with f of x is equal to 2 to the power of x. This is a typical example you'll see in your textbook. And the basic way to do this is just start out with kind of making a table of values, just like you've always done. So you know those 3 points already. You know that there's -1, comma, you're going to have 1 over the base. The base is 2, so 1/2. So that's a point. And we can go ahead and plot that. So -1 for the x and then 1/2 for the y. So that's there. And then you know you have 0 and then 1, right? If I raise 2 to the power of 0, I get 1. So the x value is 0 and the y value is 1, so that's right there. And then we know we have a value of 1 for x. That gives me a value of 2 for y, right? 2 to the first power gives me 2. So an x value of 1 and a y value of 2, so that's right there. And then I would just need to get some additional points going to make the graph clear. We know going to the left that it's going to approach the x-axis but never touch it. So I know if I chose some values, let's say I picked -2, for example, well, this is 1 over 2 squared, so that's 1/4. If I picked -4, this is 1 over 2 to the 4th power, so that's 1 over 16. Again, so on and so forth. So as this goes to the left, and I'm picking bigger and bigger negative values for x, the y values are getting closer and closer to 0, but they'll never touch it. You don't need this. You can get rid of this. You're just going to draw it to where it approaches 0 but doesn't touch it. And basically what I would do is get these points here. So just think about the integers that are left. If I go from 1 and go to 2, well, 2 squared is 4. And then I would go to 3. 2 to the 3rd power is 8. So that's enough for this guy. You can go to an x value of 2 and a y value of 4, and then an x value of 3 and a y value of 8. So that would give you enough points to sketch this graph. Again, it takes off very quickly. And with f of x equals 2 to the power of x, it's one that you can graph with your kind of graph paper. Let's look at one that takes off more quickly. So now we have f of x is equal to 3 to the power of x. And you'll notice that it takes off more quickly. Okay, so it's harder to get points here because typically you're going to work with a coordinate plane that the max y value might be 10 or 15 or something like that. If you think about 3 to the power of x, well, if I take 3 squared, that's 9, but 3 cubed is already 27. So that's way off the page, right? If you do 3 to the 4th power, it's 81. So that's just accelerating very, very quickly, right? So we know that, again, going to the left, it's the same phenomenon. It's going to approach a y value of 0 but never touch it. So we know how to draw that part. And then for the ordered pairs, again, I would just start with what we know. -1 and then 1 over the base, so 1/3. 0 and then 1, 1 and then 3. And then you could do 2 and 9, okay? But that's basically where you'd stop because, again, if you do an x value of 3, you're going to get a y value of 27. You could maybe do that on a graph paper if you started really, really low, okay, and you didn't really include this. Then maybe you can get to that, but that's still pretty hard to do. We have -1 for the x value and 1/3 for the y value. And we have 0, 1. So 0 for the x value, 1 for the y value. And then 1 for the x value, 3 for the y value. And then 2 for the x value and 9 for the y value. So that's enough points to get an idea of what this guy looks like and sketch your graph. All right, let's talk about some reflections now. So we understand what a reflection is. We get that if you have a graph that's f of x and then g of x is defined as the negative of f of x, this is a reflection across the x-axis. And then if g of x is equal to f of negative x, this is a reflection across the y-axis. So in this case, we have a reflection across the y-axis. We can see that. And so what's going to happen is I'm going to define f of x as 2 to the power of x. And then g of x is going to be f of negative x. So basically, we could say g of x is equal to 2 to the power of, I'm just plugging in a negative x in the place of x. So this is going to be a negative x up here. Now, there's another way to look at this, and I'll talk about this. I'm going to graph this separately in a moment. But right now, let's just think about it as a reflection. So we already know these points because we already graphed this before. So you have this 3, 8. You have this 2, 4. You have this down here, which is 1, 2. And then over here, you have this point here, which is 0, 1. That's going to be on both of them. And then lastly, you have this one, which is going to be -1, 1/2. So to reflect this, I'm going to keep the y value the same. So over here, the y value is the same, but the x value will be its opposite. So you'd have -3, right? Just change 3 into -3, and then the y value is the same. Then this point over here. So the y value is the same, so it's 4. And then I'm going to change the x value into its opposite, so just -2. And then down here, so on and so forth, it would be -1, 2. And it's kind of hard to fit that in there, so let me just try. So -1, 2. And then if I go down here, this guy gets flipped over. So this would be +1 and then 1/2, okay? And then you have this point here that's on both. So you have that 0, 1 that would be on both. So if you wanted to graph this without reflecting it, it would be fine. You could do f of x is equal to 2 to the power of -x. And realize that this guy could be graphed in its current state, or you could kind of manipulate this with exponents. And you could write this as 1 over 2 to the power of x. And 1 to the power of x would still be 1. So I could really say this is 1 to the power of x over 2 to the power of x. And I can now write this as 1 over 2, all raised to the power of x. Okay, so you can look at it this way or this way. Let me just kind of erase all this. This is just getting us there. Whichever way you find to be easier, I'm just going to work with it in this format. So kind of getting some ordered pairs going. I know my 3 points are going to be available to me. So my -1 and then 1 over the base. The base is 1/2, so 1 over 1/2 is 2. I know my 0, 1 is there, right? 0 for x, 1 for y. And I know my 1 and then the base is 1/2, so that's there. So those are my 3 points. Now, this guy is an example of where in nature we would say it's a decay graph. Okay, so it starts out high and goes low. The other ones are a growth graph, right? They start out low and they go high. So in this case, what I'd want to do, if I want to get some points up here, kind of going up, I need to go in the negative direction in terms of x. So I would go something like -2 and -3. And of course, we know that if we plug in a -2 there, 1/2 raised to the power of -2, through the rules of exponents, we know that would be 2 squared, right? That's all that is, which is 4. So this would be 4, and the same thing, 1/2 raised to the power of -3, through the rules of exponents, we know that would be 2 to the power of 3, or 8. So we saw this by reflecting it, but we see it by kind of plugging in the points here. It's the same thing. So if you want to kind of plot these, let's start with the 0 for x and 1 for y. And then we have that an x value of 1 would give me a y value of 1/2. And let's kind of go to the left now. So we would have an x value of -1, which would give us a y value of 2. And then an x value of -2 would give us a y value of 4. And an x value of -3 would give us a y value of 8. So again, that's another way you could sketch the graph of this guy. Once you have your points plotted, you could sketch this down like this. And of course, it's going to approach a y value of 0, but again, not touch it. So these are always going to approach the x-axis, but not touch them. In the case of a decay graph like this, it's going to approach it coming to the right. If you go back to your example with the growth graph, you see that it approaches it as you go to the left. So it starts out small if you're coming from the left and going to the right, and then it grows like this. So this is a growth graph. And again, because this one starts out high and comes down, this is a decay graph. All right, let's look at another reflection. So this guy is going to be reflected across the x-axis. So we know that, again, if we would define something like f of x to be equal to, in this case, it's going to be 3 to the power of x, well, then my g of x here, if it's reflected across the x-axis, it's defined as the negative of f of x. So in this case, it would be the negative of this. So the negative of 3 to the power of x. So let me just erase this and put the negative of 3 to the power of x. And of course, now we're reflecting the points across the x-axis. So what happens is the x values stay the same, but the y values are now made into their opposites. So if I have this point here, which is 2, 9, and I reflect it across the x-axis, it becomes, again, 2, -9. So the x value now stays the same. The y value gets turned into its opposite. Similarly, this point right here, which is 1, 3, is going to become what? It's going to become 1, x value stays the same, and then -3. Then this point right here, which is 0, 1, so this is 0, 1, is going to get reflected across, and it's going to become 0, -1. And then this last point here, which would be -1, let me write this over here. So -1, 1/3 would be reflected across. So it's still an x value of -1, but now the y value is going to be -1/3. Okay, so on and so forth. So you can see that's a good way to kind of reflect it and sketch the graph. You could also graph this guy on its own. You don't need to reflect it. So let's say g of x, or you could say f of x, it doesn't matter. It's the negative of 3 to the power of x. Now you got to be careful here because basically you're taking, in terms of the y values that you're used to, and you got to make them negative. So those 3 points that you're kind of working with all the time, the -1 for x, and then the 1 over the base, well, now you got to make that negative. So instead of 1/3, it's got to be -1/3. Okay, so you got to keep that in mind if it's a reflection. And then if I had 0, 1, well, now it's 0, -1. If I had 1, 3, well, now it's 1, -3, so on and so forth. So I can do my 2 here, but now instead of getting 9, I get -9. Okay, so just keep in mind that you can work with the normal x values, but you've got to make the y values into their opposite. So again, just taking these 4 points, if I do -1, -1/3, that's there. 0, -1 is right there. 1, -3 is right there. And then 2, -9 is right there. So again, that's enough to sketch your graph. You know this guy going to the left is going to approach the x-axis but not touch it. And coming to the right, we're just going to go through those points. And again, you just draw a smooth curve, put an arrow at the end. All right, so I want to do one more of these. This is pretty typical in this section. We looked at some reflections, but you're also going to have horizontal and vertical shifts like we talked about earlier. So let's say f of x, which is my guy in yellow, is going to be 2 to the power of x. We already know that graph. We're comfortable with it. Now let's say we have g of x, and this is equal to 2 to the power of x plus 1, and then minus 1 over here. Okay, so we're going to have a horizontal shift 1 unit to the left. That's what that plus 1 is going to do right there. Let me highlight that. And you're going to have a vertical shift down by 1 unit. That's what that minus 1 is going to do. Remember how you think about this. We could say that g of x is equal to f of, in this case, it would be x plus 1 and then minus 1. Okay, so what's happening is this plus 1 here, again, you've got to think about the opposite of that if it's getting plugged in for x. So to undo that, this is the one that confuses everybody. So if it's associated with x, you undo it. So the plus 1, you got to go minus 1 to undo it. So it's a shift to the left. Let me just do this. Shift to the left by 1 unit, okay? And then this one that's outside of the function, this minus 1, this just directly affects the y value. So we're just shifting down by 1 unit. So we'll say down by 1 unit, okay? So if you've got a graph of f of x equals 2 to the x already drawn, and you just want to kind of shift this guy down by 1 unit and to the left by 1 unit, it's pretty easy to do. So just get your points going. So this point right here, which is 3 for the x value and 8 for the y value, gets shifted 1 unit to the left and 1 unit down. So now what is this going to be? Let me write this over here. Well, the x value is left by a unit, so it's 1 unit less, so it's 2. And the y value is 1 unit less, so it's 7. Then if I take this point right here, which is 2, 4, again, if I shift it, it goes 1 unit to the left and 1 unit down to get me right there. And so that is going to be 1, 3. Then if I take this point right here, which is 1, 2, again, if I shift this 1 unit to the left and 1 unit down, it ends up being what? 0, 1. Now that ends up intersecting with another point that's there, so that's a little bit confusing. But this point is already there on the original one, and that point of 0, 1 gets shifted down. So let me write this twice. So let me put 0, 1 over here. So this 0, 1 that's on the graph of f of x equals 2 to the power of x would get shifted 1 unit to the left and 1 unit down. So that's this guy right here, okay? That's crossing through the x-axis. And basically that's going to be what? It's going to be negative 1, 0. And then lastly, if you can see, I have this last point here, which is negative 1. And let me just draw an arrow for that one. So it's negative 1, 1/2. Well, that's going to go 1 unit to the left and 1 unit down. So that's going to be what? Negative 2, comma. And then if I took 1/2 and subtracted away 1, I'd be at negative 1/2. Okay, so I know this is messy, but again, if you're trying to show these kind of reflections or shifts or whatever it is, you just want to kind of mark things up and draw your other graph. It doesn't have to be perfect. You just want to show the teacher that you understand what's going on.